the simplest experiments that I love, that would be a simple calorimeter, physics or chemistry lab. You can measure the specific heat of a compound. You can measure maybe how the density changes. We might be able to measure the heat of vaporization, determine the phase space with a thermometer or something. Simple thermodynamical properties. We're going to get those right, at least to within the experimental certainty, at the cost of not having any insight whatsoever in the molecular detail. We won't get a structure of it from that. But if we want the structure, maybe we should use X-ray crystallography. Well, X-ray has other problems. You don't get X, Y, and Z coordinates from the X-ray. You get structure factors, reciprocal space patterns. Remember the DNA pattern from the 1950s, right? And how that turned into DNA. It was not trivial. You need a model to interpret that into a structure. The second problem is that if you're interested in proteins at room temperature, well, this is a structure at 100 Kelvin. What says that they are the same? They're certainly not moving the same way. So you get, in theory, an unprecedented detail here, but there are other approximations that might or might not be severe, and there is certainly some modeling involved to get to those structures. NMR. I know I've been knocking NMR a little bit when I said that it's not my method of choice for determining structures today. That does not mean that it's bad, though. It's a fantastic method to study interactions and dynamics in proteins. The problem is that you get that by identifying resonance peaks and then assigning them. That makes structure determination extremely complicated, in particular for large proteins. And we can get dynamics, though, maybe exchange of deuterium with hydrogen or so. But again, it's a non-trivial amount of information, and I certainly don't get a full resolution of the entire protein and atomic detail. On the other hand, in contrast to X-ray, here I am at room temperature in water solution, and that's definitely something worth using. So you might start to see a pattern here that these methods have different strengths. So does cryo-EM. I'm biased, I love cryo-EM. We use it all the time. In contrast to X-ray, I don't need to turn my protein into a crystal. That's awesome. On the other hand, here I might occasionally get too much data. I need to look at hundreds of thousands of images. I need to average them. I need to classify them. I need to use computers to derive a model for a three-dimensional electron density and then model my protein structure, X, Y, Z coordinates into that density. So that's quite a bit of modeling too. The point here is not that any of these methods is better than molecular dynamics simulations. They're also not worse. They provide different types of information, and we want to use all of them for what they're best at, but avoid using them for things they're not good at. And in particular, if you compare multiple methods, either these or molecular simulations with one of these, you will be able to tell more about your system, and you will be able to avoid falling in traps because you had one method that led you astray.